Okay, so good morning, everyone. My name is Eric, and today we'll be presenting our FYDP for which we have called the GraFET, a graphene-based nano-electric harmful gas sensor. So first off, I want to take this time to thank our industrial sponsor, Perkin-Elmer, for providing us the equipment needed to go through with this project, and also our two academic consultants, Dr. Aiping Yu and Dr. Vivek Maheshwari. They've really been invaluable in this experience. So today I'll be going over a brief introduction to the team. I'll go over the problem that we are trying to solve, the solution that we have come up with, the GraFET, our initial prototype design, future directions our project will take. I'll do a brief cost and market analysis, and then followed by some conclusions. So this is the GraFET team. It's comprised of myself, Stuart, Laura, and Wenbo, who's manning the booth right now. And we are all fourth-year nanotechnology engineering students at the University of Waterloo. As you know, this program is very interdisciplinary and diverse, and has really made us ideally suited to challenge such a big project that ranges from material science all the way up to electrical engineering and a little bit of physics. So the problem we're trying to solve is pollution. As you guys know, pollution is a huge problem in the world, but what you may not have known is that 1 in 8 deaths worldwide are caused by pollution-related diseases. That's over 10%. And while you may think that these deaths are centralized in Southeast Asian communities, and I'm sure you guys have all seen pictures of Beijing, you may even think that this is a picture of Beijing right here. But it's actually not. This is a picture of Toronto that was taken last summer in the middle of the day. So this really brings it home that this is not only a problem abroad, this is also a problem in Canada. The Canadian Medical Association estimates that 21,000 Canadians died last year due to air pollutant-related diseases. Although we supposedly have some of the best air quality in the world. So how is this possible? And while it's up to policymakers and governments to change how carbon emissions are released into our environment, there is a need for the monitoring of greenhouse gases. Perkin-Elmer's ELM project offers real-time detection of greenhouse gases by placing large industrial gas sensors on the rooftops of buildings. However, this project is limited due to the scarcity and immobility of these sensors. There's a need for mobile sensors that can allow for higher resolution mapping of air quality data. The ELM project can be used by communities and companies to monitor air quality throughout their region to better establish urban and industrial development. It can be used by citizens to monitor air quality throughout the region to help them plan throughout their day. And we are introducing a third element, ELM for You, which personal exposure can really help you monitor and give higher resolution maps when these devices are networked together. Laura? So currently there is one ELM sensor in downtown Toronto, and while this does provide very meaningful information, its statistical validity starts to decay the further you are away from this sensor, meaning that if you're 1 meter away, yes, that sensor is important. However, more than a kilometer away, that data is starting to fail in terms of relevance. And this is important since these sensors are placed on top of rooftops, and it isn't accurately representing the smog and the emissions from cars that you are getting at street level. And that's the problem that we are trying to solve. Next. Is it lagging?
Yeah, it's lagging.
All right, so our solution to this problem is the GraFET. So the GraFET is a graphene-based field effect transistor. So what it is, it's just a field effect transistor that utilizes graphene as the conductive channel across it. So what is graphene? Graphene is a single layer of carbon atoms tightly packed in a hexagonal lattice. In 2010, the team that discovered graphene were actually awarded the Nobel Prize for Physics. It exhibits extraordinarily high surface to volume ratios. So if you think about a monolayer of graphene, every single atom in it is exposed. Every single atom in it is a surface atom. So they are all exposed to the graphene. There's no bulk atoms to increase the noise of our signal, So it allows, due to this extremely high sensitivity of the monolayer graphene, we're able to make low cost and low power solutions that are still sensitive enough to detect the levels of gases we're attempting to detect. So there's two methods that can be done for graphene field effect transitions. The first method of detection is dubbed the impedance detection method. So this works by you first expose your analyte gas to your graphene sensor. It'll then desorb onto the surface, You can then run a DC bias across it, and you can measure the change in current that you get out of it. This change in current obviously directly translates to a change in the resistance, and that actually has been shown to have a direct correlation to the concentration of your target gas in the atmosphere. The gas then desorbs off the surface, and you can repeat the exposure cycle again. So the main advantage to this method is when you are creating the graphene, you actually heavily functionalize it. So you can create these very specific functionalization groups that will target exactly what you're looking for. So if you want to target carbon monoxide in the atmosphere, you can target specifically carbon monoxide and eliminate signals from all other gases. The main problem with this method is that since you're using this very specific targeting method, it'll actually bind fairly tightly to these groups. And so you actually have the desorption step as the rate limiting step in your process. So what this means is it'll take up to a few minutes for the gases to desorb off the surface. So you can imagine if you're in a region of high concentration of a specific gas and you were to move into a region of low concentration, the sensor will lag by up to a few minutes. So this greatly reduces the resolution of air quality maps if you're trying to build them. The second detection method is dubbed the heterodyne detection method. So what this actually does is it uses an intrinsic piece of graphene rather than functionalized, and it sends in an AC bias that will interact with the polarity of specific molecules. So if you can imagine, if you're running an AC bias across it and the electron cloud is flipping back and forth when you run this AC bias across it, this flipping of the electron cloud will induce a polarity shift in polar molecules that approach the surface of the graphene. So as the polarity switches on these molecules near the surface, it actually induces a change in the charge density in the graphene. You can measure this change in the charge density and a change in the output current. So what's great about this method is since you've sort of got this weak interaction, you can actually get millisecond response times. So that would be perfect for building these high resolution maps that we want to build. The main problem with this method is that as we're using intrinsic graphene, it doesn't have any specificity to it. So it will interact with any polar molecule, and so you'll know that you have a signal, but you don't actually know what you are detecting. So our solution was to try to combine these two methods. We wanted to sort of get the specificity from the impedance method as well as the rapid response time of the heterodyne detection method. So our plan was to create a functionalized heterodyne sensor where we dope the graphene with some molecules to try to get more specific results with using the heterodyne detection method.
So now I'm going to talk about our actual prototype design and the results we have so far. This is a SolidWorks drawing of our device. It's fabricated on an oxidized silicon substrate, and then we use microfabrication techniques to deposit gold electrodes. And then it's actually on top of these electrodes that we deposit our graphene. These are the results of our microfabrication. You can see on the right-hand side our full device, which is smaller than the size of a dime. However, on the left, you can see an optical microscope picture of the active region, which has the largest feature size at about 20 micrometers. You can also see on the left-hand side that the electrodes aren't actually connected at this point, which is where the graphene will come in to complete the connection. So the major challenge in graphene sensing technology right now is really finding the right combination of fabrication technique and deposition method to create high-quality graphene at a low cost and using a process that can be easily scaled. So currently, graphene sensors are generally made using chemical vapor deposition in research, which is a great method. However, it is very expensive. Another method is mechanical exfoliation or the Scotch tape method, which produces a pristine layer of graphene. However, the throughput is very low. Now, for our application where we want our device to be widely distributed, we are using a unique combination of a solution-based method to fabricate the graphene and a unique aerosol deposition method that we've actually developed. So using this procedure, you can see in the coming slides that we have been able to create a highly conductive layer of graphene at a low cost, and the procedure is easy enough to be scaled. These are the results of our electrical testing. There are 3 curves because we actually have 3 prototype devices. In blue, you can see intrinsic graphene. red is nitrogen-doped graphene, and green is sulfur-doped graphene. So for this experiment, we ranged the voltage and measured the current. And you can see for the two doped cases, at high voltage, the current plateaus, which is characteristic of field effect transistor devices. And while this data is less than perfect, it is preliminary data. And based on this, we were confident that our device would perform as expected in a gas environment. This is the chamber that we designed and fabricated for our testing. It's made of acrylic, and there are two holes on either end for the gas inlet and outlet. There's also a hole on the side for probing the electrical signal. And inside, you can see our device, which is situated on an acrylic plaque that can be easily moved in and out of the chamber. On the top plot, you can see the results of a COMSOL simulation showing the kinetics of the gas flow into the chamber. And this simulation was done for 100 ppm carbon monoxide gas, which is the gas that we were testing at the highest concentration that we would be using. You can see this plot plateau at around 50 microseconds, meaning that with this setup, 50 microseconds is the minimum response time that we'll be able to measure. And we were expecting our response time to be greater than this, so this was really a successful setup for us. On the bottom, you can see the velocity distribution throughout the chamber, which just shows that the flow of gas will be constant over our device. This is our testing setup, which is normally in a fume hood, but we took all the components out so you can see them clearly. On the right-hand side, you can see two mass flow controllers. One is for the analyte gas, and one is for our carrier gas, which is nitrogen. You can also see our chamber fabricated, and there are two circuit boards for controlling the mass flow controllers. On the left-hand side is a lock-in amplifier, which we use to analyze our signal, and we monitor the signal using a LabVIEW program. So these are our exciting results for detecting carbon monoxide with our prototype. So this test was done for 100 ppm carbon monoxide, and in blue you can see the intrinsic signal, which was taken after a nitrogen baseline was established. You can also see the sulfur signal, which is 85% higher than the intrinsic signal. So this really concluded that our hypothesis was correct in that using doped graphene, you can increase the selectivity of your device.
The main issue with the use of any nanomaterials are their toxicological effects. Specifically, graphene in a powder form poses a risk to inhalation. To mitigate this risk, we designed our process so that it would be completely solution-based, and our aerosol deposition method would be enclosed to reduce the risk that graphene is aerosolized and would be breathed in. Once annealed to the substrate, by heating the substrate to 100 degrees, the graphene is stuck to the surface and does not pose an environmental or health threat throughout normal device operation. For the testing purposes of our gases, strict safety regulations must be met. So for that situation, we used carbon monoxide, which is the least toxic gas that we could get our hands on. Obviously, in the future, we would like to expand this to get more dangerous gases. However, that's more hoops to jump through. Now, while we're still in the prototyping phase, there are many other steps before product launch. First off, we must complete preliminary gas testing, including determining our detection limit and our dose response. Also, we must conclude temperature and humidity testing, since that will be a part of normal device operation and is worth measuring. Next, we will hire some electrical engineers to do some smartphone integration for us, to integrate this into either smartphones or wearable electronics. We will also work on creating a mobile networking app for networking all these devices together to create a high-resolution air quality map using these devices. Throughout this entire process, we will be extending our gas library and the functionality requirements so that we can increase our array of devices and the specificities required. Now that we've gone over the technical feasibility, here's a little economic feasibility. Today's smartphones are ubiquitous. Nearly 2/3 of US adults own a smartphone, growing at 25% year over year. By the year 2020, over 70% of the world's population will be using smartphones. Our initial market that we are trying to target is the wearable electronics industry, such as Fitbits, since the consumer of Fitbits are usually health-conscious users who would benefit from having an air quality monitor in their device. Currently, the wearable electronics industry is valued at $20 billion and is expected to grow to $70 billion by the year 2020. Once our technology has matured and we have proven its validity, we will move on to the smartphone market, which is currently estimated at 260 and expected to grow to just about $700 billion by the year 2020. Now, we've shown that there's room in these markets for a new and innovative technology, but how does our technology fit in? At a cost of roughly less than $3 per device, our solution is definitely economically feasible. But to make this more apparent, we've split our cost breakdown into two columns: cost per unit and cost per device. Cost per unit is the cost per silicon wafer, which range from the size of a CD to a large dinner plate. We can array close to thousands of devices, since they're the size of TV pixels, onto a single silicon wafer. Through this and our solution process method and aerosol deposition, we're able to keep our costs low. So in conclusion, we have developed a novel nano-electronic sensor capable of both rapid, sensitive, and specific detection of gases. Due to their small size, they can be conveniently integrated into smartphones for real-time monitoring. By networking these devices together, we can create high-resolution air quality maps of our cities. We are moving towards a trend where more and more technologies are fit into our already compact devices. A nano-electronic sensor capable of measuring air quality data could just be the next big innovation. Thank you.
Okay, now the session is open for questions.
Yes.
So how do you exactly retune a sensor to detect other types of gases? So physically it's the same sensor. But how do you actually adjust it so that you can tell if this is one type of harmful gas versus another?
Yeah, well, by figuring out the different specificities that are required, we're hoping to create different specificities by doping different arrays. So we can create an array of sensors that have different signals.
Different dopants.
Yeah, different dopants. So that will definitely be a challenge to manufacture different dopings of graphene in a single area. However, if you have multiple of these and they exhibit really high or really low sensitivities to certain gases, then we could figure out what's in the air.
So when you foresee integration into like a cell phone, you'd actually have to physically have different types of sensors for different gases, so it becomes sort of a physically larger sensor chip.
Yeah, we would have to work on definitely miniaturizing that, but once again, that is like currently on our one device, we have six different arrays on our one chips there. If we can find a way to dope different arrays with different dopants, then that would solve that problem. But that definitely is a concern in getting all of these into one area.
Follow-up question. Follow-up question to that. So that's going to take a while to develop. If I understood you correctly, in the short term, you could just put a heater underneath this, a microheater, to temperature cycle to get your discrimination happen. And then longer term, develop these selective sensors.
Yeah, we could do something similar to that. Yeah, that's a good
So
idea.
it's not just wait 5 years. It's you can do something now. You can develop better sensitivity later.
Yeah, that's a good idea.
How do the sensors compare with the electrochemical sensors which are available in the market today?
Oh, pardon me?
I think the electrochemical sensors which are available in the market today, about $2 to $3.
Yeah, well, the problem with electrochemical sensors right now is that they have a very long response time. So it could take a couple minutes for these to absorb and desorb these gas molecules, which is not very beneficial because since, like, for example, if a truck passes by you and spews a whole bunch of nitrous oxide in your face, then your sensor won't, if it's electrochemical based, it may or may not pick up that influx of gas molecules, or it may average it out to a specific time. So by sampling, by running it in a heterodyne method, we're able to sample more frequently and get a better, more accurate measurement of what's coming at you.
And how do you differentiate with the particulate matter? Because 0.3 micron particulates are also mostly polar in the air.
Yeah, tackling that small change between the particulate. Right now, we're just looking at the vapor molecules, not necessarily particulates.
But they are particulate matters. In fact, a lot of the harmful gases are attached to the particulates.
Yeah, that's something we'll have to look into, how it reacts to particulates in the atmosphere, and varying sizes, of course. That'd be interesting to do. Yeah, that's a good count. Thank you.
How did you integrate the graphene onto the chip? You sort of said very quickly that there was some spray process.
Yeah, so we used an aerosol deposition method. So you ultrasonicate the graphene in solution, and then you spray it to the surface and anneal at 100 degrees. So we did a optimization to figure out what concentration worked best. We also tried a drop method where we put a drop of the solution, but really there was too much graphene.
So there's the suspension of graphene in water, I guess?
In ethanol.
Acetone.
In a
Oh,
solvent?
yeah.
Yeah, in a solvent.
So it's just pure solvent?
Yes.
Okay, and then you take like an airbrush and spray it on, or what's the?
Perfume
It's like
sprayer.
a perfume, like a
Oh, okay,
commercial
okay. So
perfume
it's just-
dispenser,
so you-
glass
okay.
one. Yeah.
And so like, there's a lot of graphene on this surface,
Mhm.
right?
Right.
It's just a matter of chance, but you get something on the electrodes here.
Yes.
Yeah.
And then, but how do you know how much surface you have in terms of the graphene that's actually, is there a bunch of layers of graphene stacked on top of each other, or is it a single monolayer of graphene? Or
That's
how
sort
do
of
you-
one of the trade-offs in our design is that, with the CVD method, you can get that
Right.
mono layer, and it's this really pristine, perfect
Right.
layer, and they can actually get part per billion levels of detection
Okay.
using the CVD
So
method.
did you see a
ours,
variation in
Uh,
different chips because of this sort of?
Yeah, when we were going
integration
for,
process?
when we tried, spraying on these low concentration in our hopes of, if you have a low concentration, you have more probability of getting these single layer sheets, but then we wouldn't get a connection across the electrodes. So just this method is inherent to having multiple, facets and stacks of graphene.
So
However,
the yield goes up, but the sensitivity goes down.
we lose
Yeah.
a bit of it, but we're not looking at that part per billion level. We're looking at more around part per million. So it was,
So you have a range that you can maintain
Yeah, so
with a high yield.
yeah.
Just another question.
How challenging is it to incorporate the other components into the phone? Like you're using a pretty large impedance analyzer and a locking amplifier. Are these components that you can easily put into your phone?
well, the reason why the lock-in amplifier is so huge, other than it being made pre-1980, is because it's meant to range a wide range of frequencies. So we'll be focusing on one frequency, which will hopefully bring down the size. Obviously, we're not computer engineers here, where we tackled the materials aspect of it, but that's definitely something that we're hoping to minimize and use onboard electronics on the phone already to help reduce the size of our device. What was your question?
Just a quick question. Why would you rather go and integrate yourselves with cell phones and other devices? Why wouldn't you just make a standalone device which can connect to a cell phone through Bluetooth or other Wi-Fi connectivity?
Well,
That way it would be bootable, it would be still not tied to a cell phone per se.
yeah, that's definitely something we'd have to look into. We were looking at, because right now they do have on the market these kind of, they look like flashlights, and they are air quality monitors, and they do have Bluetooth and everything. However, that we think is just inconvenient if you have to drag around an extra device. If it was already built into your phone, like a GPS or something, then more people would be prone to having it than if it was, on a keychain or something like that. But yeah, that's definitely something that, yeah.
It would be
You'll have to convince the manufacturers to put it.
Yeah. It was
Yeah.
It was more of a marketing reason as opposed to anything to do with the functionality of the device.
Okay, so we are a little bit behind the schedule. I think let's stop here today, and let's thank the speaker once again.